The morning of August 17th, 1944. Somewhere over the Yawata steel works on Kyushu, a massive American bomber trailing smoke from its No. 3 engine fought to maintain altitude. The crew of the B-29 Superfortress, 29,000 feet above enemy territory, had just released their bombs when Japanese anti-aircraft fire found its mark. Captain James Harrington ordered his crew to bail out, and the enormous aircraft, all 65 tons of American industrial might, began its descent toward the Japanese countryside below. What followed was not what the Americans intended, but it would become one of the most consequential intelligence operations of the Pacific War. Japanese recovery teams descended on the crash site within hours. They were not looking for survivors. They were looking for secrets, and what they found in the twisted wreckage of that bomber would shake the foundations of everything Japanese engineers believed they knew about aircraft manufacturing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is not a story about a single airplane crash. This is a story about the moment when Japanese technical intelligence officers, standing among scattered fragments of American aluminum, realized they were not fighting an enemy with better tactics or more resources. They were fighting an enemy whose industrial civilization had evolved beyond anything Japan could match. The B-29 Superfortress was not merely an aircraft. It was a message written in metal, a declaration that American manufacturing had achieved something unprecedented in human history, and the Japanese engineers who examined its remains became unwilling witnesses to their own nation's industrial obsolescence. Today, we explore how fragments of a crashed bomber became the mirror in which Imperial Japan saw its future and found only the inevitability of defeat. Staring back, the Boeing B-29 Superfortress first flew on September 21, 1942. Designed to strike Japan from bases thousands of miles away, it was by every measure extraordinary. Weighing over 70,000 pounds empty and nearly 65 tons fully loaded, it was the heaviest bomber in operational service. Its four Wright R-3350 duplex Cyclone engines, each producing 2,200 horsepower, could push the massive aircraft to 35,000 feet and speeds exceeding 350 miles per hour. It carried 10 tons of bombs over distances of more than 3,000 miles, but the B-29 was not impressive because it was large. It was impressive because it represented a fundamental reimagining of what mass-produced military equipment could be. The aircraft featured innovations that belonged more to science fiction than to 1940s engineering reality. Full cabin pressurization allowed crews to operate in shirt-sleeve comfort at altitudes where the outside air would freeze exposed skin in seconds. Remote-controlled gun turrets, directed by an analog computer fire control system, meant gunners could defend the aircraft from climate-controlled positions deep inside the fuselage. Two separate radar systems allowed bombing through cloud cover too thick for human eyes to penetrate. This was not incremental improvement. This was discontinuous technological leap, and every one of these systems had to work flawlessly while being produced in massive quantities by a workforce that had never built anything remotely this complex. By the summer of 1944, when B-29 seconds began appearing over Japan in numbers that grew with each passing month, the Japanese understood they faced a serious threat. What they did not understand was the magnitude of the industrial gap the bomber represented. Japanese pilots reported that American bombers seemed impervious to damage that would destroy Japanese aircraft. Japanese intelligence officers noted that even heavily damaged B-29 seconds often made it back to base. Japanese anti-aircraft crews despaired at hitting targets flying far above the effective ceiling of most interceptors. But these were tactical observations. The strategic reality remained hidden until Japanese engineers got their hands on actual wreckage. The truth that Japanese metallurgists discovered was more devastating than any bombing raid. When they analyzed the aluminum alloys used in the B-29's airframe, they found material with strength-to-weight ratios that should not have been possible at mass production scale. American engineers were using aluminum alloy 2024, a copper-aluminum alloy that had become standard in American aircraft production. But the quality control the Americans achieved was unprecedented. Japan had developed extra super duralumin, an aluminum zinc magnesium copper alloy created by Sumitomo Metals engineer Dr. Igarashi in 1936. This alloy, designated ESD, actually exceeded the strength of standard American duralumin. It was used in the Zero fighter's wing spars and represented genuine Japanese metallurgical innovation. In pure technical terms, Japanese metallurgists understood advanced alloy theory as well as anyone in the world. But understanding metallurgy and manufacturing aircraft were entirely different problems. The American manufacturing process for the B-29 revealed the true nature of the industrial chasm. Every aluminum panel in the bomber was produced to tolerances that Japanese factories, bombed constantly and struggling with raw material shortages, could no longer reliably achieve. The rivet holes aligned perfectly. The rivets themselves, 600,000 per aircraft, were installed with consistent precision. There were no tool marks on finished surfaces. The fit and finish of components suggested they had been handcrafted by master artisans. They had not been handcrafted. They had been mass-produced by workers who had never touched an aircraft before the war began. This was the revelation that broke Japanese technical confidence. Consider the B-29's wing. Each wing was a masterpiece of aerospace engineering, built in 3 sections that had to mate together with perfect alignment. The spar, the wing's primary structural member, was machined from solid aluminum forgings that weighed thousands of pounds before machining and ended as precisely engineered structures where every gram mattered. Japanese engineers measured the tolerances and found them breathtaking. American factories were holding dimensional accuracy measured in thousandths of an inch across components spanning dozens of feet, and they were doing it thousands of times over. The Japanese had designed brilliant aircraft. The Zero's long range and maneuverability came from ruthless weight optimization and sophisticated engineering. But Japanese aircraft were built by skilled craftsmen, working to close tolerances through intensive manual labor. Each Zero required meticulous hand-fitting of components. Each aircraft took hundreds of hours of skilled labor to complete. The B-29 took 33,000 man-hours to build. This sounds like a lot until you understand that Boeing, Bell, and Martin were producing these enormous, complex machines at combined rates exceeding 300 per month by 1945. The Americans had achieved what Japanese industry thought impossible. They had mass-produced complexity. The quality control systems the Americans employed were more advanced than anything in Japanese industry. Statistical process control, developed by American engineers like Walter Shewhart and W. Edwards Deming, allowed American factories to maintain consistent quality across millions of components produced by largely unskilled workers. The Japanese approach relied on skilled craftsmen inspecting each component individually. The American approach used mathematics to ensure the manufacturing process itself produced consistent results. When Japanese engineers examined the B-29's electrical system, they encountered another shock. The aircraft contained 9.5 miles of wiring, 9.5 miles of copper wire, all insulated to exacting specifications, all routed through the aircraft in complex harnesses that had to be installed correctly, despite the involvement of dozens of different workers at different stages of assembly. The wiring diagrams for the B-29 filled volumes. The documentation required to build and maintain the aircraft represented an information management challenge as sophisticated as the engineering. Yet Boeing's plants were producing these aircraft faster than Japan could produce simple fighters. The hydraulic system operated at pressures Japanese engineers considered dangerously high. American metallurgy and seal technology allowed the B-29's hydraulics to function reliably at pressures that would cause Japanese systems to fail. The turbo superchargers that gave the B-29 its high-altitude performance were machined to tolerances. The Japanese struggled to replicate in laboratory conditions, yet the Americans were manufacturing them by the thousands. Every system in the aircraft whispered the same devastating message. American industrial capacity had reached a level where they could afford to over-engineer everything and still produce more aircraft in a month than Japan could produce in 6 months. More importantly, they could do it with better quality control than Japanese factories using hand-picked components. but the metallurgy of the airframe itself represented the cruelest revelation. Japanese metallurgists had developed ESD precisely because they understood advanced aluminum alloys. Dr. Igarashi's work was world-class. The Zero's structural alloys were, in some respects, more advanced than what the Americans used early in the war. Japanese engineers took pride in this achievement. What destroyed this pride was not discovering that American alloys were better. It was discovering that American manufacturing processes were so superior that even with theoretically equivalent materials, the resulting aircraft were in different categories entirely. The aluminum panels in the B-29 showed no warping, no inconsistent heat treatment, no variations in thickness or material properties. Japanese metallurgists knew these panels had been produced in enormous quantities. They knew the Americans were building these bombers in 4 separate factories, each producing dozens of aircraft per month. They knew that Boeing's Wichita plant alone employed over 30,000 workers. And they knew that maintaining this level of quality control across such massive production scale required industrial capabilities Japan simply did not possess. Consider what this meant. The Japanese had access to the metallurgical science. They understood the chemistry and the heat treatment processes, but they lacked the industrial infrastructure to implement this knowledge at scale with consistent results. Their factories had been designed around craft production methods refined over decades. American factories had been designed around mass production from the beginning, with quality control systems built into every stage of the process. The truth was even more painful. Japanese engineers examining B-29 wreckage were not looking at cutting-edge experimental prototypes. They were looking at standard production aircraft, one of thousands, built by workers in Kansas or Nebraska or Washington state, many of whom had been farmers or housewives 18 months earlier. The industrial system that produced these aircraft had transformed ordinary Americans into precision manufacturing workforce in the time it took Japan to train a single skilled craftsman. This was American manufacturing philosophy made manifest. Build the machines that build the machines. Train the workers using systematic methods. Employ statistical quality control to maintain consistency and accept nothing less than excellence even from mass production. The Japanese approach optimized for skilled workers producing small numbers of excellent machines. The American approach optimized for systems that could produce excellent machines regardless of individual worker skill. The B-29 forced Japanese engineers to confront an uncomfortable question. What happens when your enemy's industrial philosophy is fundamentally superior to your own? What happens when you realize that all your craftsmen, all your skilled labor, all your traditional manufacturing excellence cannot match a system designed from first principles to mass-produce quality? The answer was written in the growing formations of B-29 seconds that appeared over Japan throughout 1945. More bombers every month, more precise strikes, more cities burning. And nothing Japan could do to stop them, because the industrial capacity gap was not closable through effort or determination or sacrifice. The industrial philosophy, embodied in the B-29, challenged every assumption Japanese military planners had made about modern warfare. Japan had entered the war believing that superior training, tactical innovation, and warrior spirit could overcome material disadvantages. The Zero fighter had seemed to prove this thesis. Designed for extreme range and maneuverability through radical weight reduction and meticulous craftsmanship, it had dominated the early years of the Pacific War. Japanese pilots, trained to extraordinary proficiency through years of rigorous instruction, had achieved kill ratios that seemed to validate the entire Japanese approach to military aviation. But the Zero's design philosophy contained a fatal flaw. By sacrificing pilot protection for performance, Japanese engineers had created an aircraft that required its pilots to survive long enough to become skilled. When American fighters with armor plate and self-sealing fuel tanks entered combat, the mathematics of attrition warfare began working against Japan. Skilled pilots died, and Japan discovered it could not replace them fast enough because the training pipeline required years to produce expert aviators. The B-29 represented the opposite philosophy. American engineers had designed an aircraft that brought crews home. The bomber carried armor plate that weighed more than some Japanese fighters' entire airframes. It had redundant systems because American factories could build redundancy faster than Japanese factories could build simplicity. It had self-sealing fuel tanks that could absorb machine gun fire and keep flying. American pilots were expected to survive their missions and fly again tomorrow, and the aircraft was engineered to make that survival possible. Japanese intelligence officers who interrogated captured B-29 crews discovered another disturbing fact. American bomber crews received only months of training before being sent to combat. They were not the elite of American aviation. The truly exceptional pilots flew fighters. The bomber crews were simply competent young men who had learned to operate an extremely sophisticated aircraft in a remarkably short time. This was possible because the B-29 was designed to be operated by normally skilled crews. The automation, the redundant systems, the thoughtful crew layout, all reflected a design philosophy that assumed operators of average ability rather than elite proficiency. This was industrial democracy's answer to warrior elitism. Build systems that work with ordinary people, then produce those systems in numbers that overwhelm the enemy's elite forces through sheer scale. Japanese engineers examining B-29 wreckage found evidence of this philosophy in unexpected places. The maintenance provisions in the aircraft's design revealed that American engineers had anticipated field repairs under combat conditions. Access panels were positioned for easy removal. Systems were designed with modularity that allowed a component replacement without extensive disassembly. The technical manuals that occasionally survived crashes were revelatory in their systematic completeness. American technical documentation approached aircraft maintenance as a systematic engineering discipline. Every system had detailed troubleshooting procedures. Every component had specifications for acceptable wear limits. Every repair had step-by-step instructions complete with torque values for fasteners and testing procedures to verify proper function. This documentation assumed maintenance crews of moderate skill following procedures, not master technicians applying craft knowledge accumulated through years of experience. The Japanese maintenance approach relied heavily on experienced crew chiefs who understood their aircraft intimately through long association. This worked well when those crew chiefs survived. But as the war progressed and experienced personnel were killed, Japanese maintenance effectiveness declined precipitously. The Americans had designed a system that worked regardless of personnel turnover. They could train new maintenance crews in weeks and achieve acceptable results through systematic procedures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Manufacturing capacity told the larger story. By 1944, American aircraft production had reached levels that Japanese planners had considered impossible. Boeing's Wichita plant was producing B-29 seconds at rates exceeding 100 per month. Bell's Marietta plant was ramping up towards similar production rates. Martin's Omaha facility was coming online, and this was just B-29 production. American factories were simultaneously producing B-17 Flying Fortresses, B-24 Liberators, P-51 Mustangs, P-47 Thunderbolts, and dozens of other aircraft types in quantities that dwarfed Japanese output. The numbers were stark. In 1944, American factories produced more than 96,000 aircraft. Japanese factories produced approximately 28,000. But the disparity in capability was even greater than these numbers suggested. American aircraft were, on average, significantly larger and more complex than Japanese aircraft. A B-29 represented vastly more industrial capacity than a Zero fighter. American factories were not just producing more aircraft, they were producing more capability by an even larger margin. The aluminum consumption figures told the story with brutal clarity. In 1941, Japanese aluminum production stood at roughly 71,000 metric tons. American production exceeded 300,000 tons. By 1944, when Japanese production peaked at 151,000 tons, American production had reached 920,000 tons. The Americans were producing 6 times more aluminum, and they were using it to build aircraft with quality control Japan could not match. This was not a gap Japan could close through effort. The industrial infrastructure required to support mass production at American scale required decades to build. The machine tools, the training systems, the supplier networks, the quality control frameworks, all of these represented accumulated industrial capital that could not be improvised or captured or bought. Japan had industrialized rapidly in the late 19th and early 20th centuries, but its industrial development had followed a different path. Japanese industry excelled at craft production of high-quality goods in moderate quantities. American industry had evolved toward mass production of standardized goods in enormous quantities. Neither approach was inherently superior. In peacetime commercial markets, both models could succeed, but in total war, where the side that could produce more weapons faster held enormous advantages, the American model proved devastatingly effective. The B-29's engines exemplified the challenge Japanese engineers faced. The Wright R-3350 duplex Cyclone was a monster of an engine, an 18-cylinder radial producing 2,200 horsepower. The engine was not without problems. It ran hot, particularly during climb-out after takeoff, and early versions were prone to catastrophic fires. But American engineers identified the problems systematically, implemented fixes, and continued production. By late 1944, engine reliability had improved dramatically through hundreds of detailed modifications to cooling systems, valve designs, and manufacturing processes. Japanese engineers, examining R-3350 engines recovered from crashed B-29 seconds, found manufacturing quality that their own factories struggled to replicate. The cylinder barrels showed no tool marks. The valve seats were ground to mirror finishes. The internal passages were deburred with a precision that suggested hand finishing, yet these engines were being produced by the thousands. The tolerances were so tight that components from different engines could be swapped without hand-fitting. This interchangeability represented a triumph of manufacturing engineering. American factories had achieved component tolerances so consistent that parts manufactured in different facilities at different times by different workers could be assembled without modification. This was the essence of mass production. Design components to specifications so precise that individual fitting becomes unnecessary, then manufacture those components with quality control systems that ensure specification compliance. Japanese aircraft engines required extensive hand-fitting of components during assembly. Skilled mechanics would carefully match pistons to cylinders, adjust valve clearances, and balance moving parts to achieve acceptable engine performance. This produced excellent engines but required significant skilled labor per engine. The American approach eliminated most hand-fitting through superior manufacturing control, allowing less skilled workers to assemble engines that met or exceeded performance specifications. The strategic implications were profound. American factories could train new workers in weeks and achieve acceptable production quality through systematic processes. Japanese factories required skilled craftsmen whose training took years. As the war consumed Japan's skilled industrial workforce, production quality declined because the system depended on individual expertise rather than systematic processes. Nowhere was this clearer than in the B-29's aluminum panels. Japanese metallurgists could measure the alloy composition easily enough. The material specifications were not secret, but when they examined how the panels were formed, heat-treated, and finished, they found consistency that revealed sophisticated process control. Every panel showed the same material properties. Every panel had the same surface finish. Every panel was exactly the specified thickness within tolerances measured in thousandths of an inch. This consistency at scale represented something Japanese industry had not achieved. Japanese factories could produce excellent individual components when master craftsmen applied their skills to each part, but maintaining this excellence across thousands of identical parts produced by many different workers required systems and processes that Japanese industry lacked. The American approach to quality control was fundamentally statistical. American engineers like Walter Shewhart had developed statistical process control in the 1920s and 1930s, and these methods had been widely adopted in American manufacturing during the war mobilization. The basic principle was elegant. Instead of inspecting every finished part to find defects, monitor the manufacturing process itself to prevent defects from occurring. Sample parts at regular intervals, measure key dimensions, plot the measurements on control charts, and adjust the process when measurements drift outside acceptable limits. This approach required understanding manufacturing as a statistical system rather than as craft production. It required training workers to follow standardized procedures and use statistical methods to maintain process control. It required investment in measurement equipment and quality control infrastructure, but it delivered consistent results at high production rates with relatively modest worker skill requirements. Japan's industrial culture had not embraced statistical process control. Japanese manufacturing excellence derived from skilled craftsmen applying judgment and expertise to each component. This approach worked brilliantly for producing small numbers of high-quality goods. It could not scale to the production volumes required for total war against an industrial superpower. The B-29's manufacturing story revealed another American advantage: systematic technical documentation. Boeing engineers had created complete manufacturing specifications for every component and subassembly in the aircraft. These specifications detailed dimensions, tolerances, materials, manufacturing processes, inspection criteria, and acceptance standards. Suppliers could manufacture components to these specifications without extensive consultation with Boeing engineers. Assembly workers could install components by following detailed work instructions without needing to understand the engineering principles underlying the design. This standardization enabled geographic distribution of production. Boeing's plants in Seattle, Renton, and Wichita built B-29 seconds. Bell's plant in Marietta, Georgia built them. Martin's plant in Omaha, Nebraska built them. Each plant received the same specifications and produced aircraft that met the same standards. Components manufactured in Kansas fit aircraft assembled in Georgia. This required extraordinary discipline in documentation and process and control, but it allowed American industry to leverage its continental scale. Japanese industry remained centralized in geographic clusters around Tokyo, Osaka, and Nagoya. When American bombing began targeting these industrial centers, Japan lost the ability to distribute production geographically. The concentrated industrial model that had worked well for craft production became a fatal vulnerability when facing strategic bombing. More fundamentally, Japanese technical culture had not developed the systematic documentation practices that enabled American mass production. Japanese engineers often worked from less detailed drawings, expecting skilled craftsmen to interpret design intent and make appropriate manufacturing decisions. This worked when those craftsmen were available, but became problematic when experienced personnel were killed or when production needed to scale rapidly. The Soviets would learn these same lessons when they reverse-engineered captured B-29 seconds after the war. Soviet engineers photographed and measured over 105,000 parts. They generated 40,000 detailed drawings. They discovered that exact copying required them to adopt American manufacturing standards because the B-29's design assumed specific production capabilities. The Soviets had to modify their entire aluminum production system because American aluminum came in different gauges from Soviet aluminum. They had to retrain workers and restructure production processes because the B-29 assumed manufacturing capabilities Soviet industry had not developed. If the Soviets, with their massive industrial base and captured examples to study, struggled to replicate the B-29, Japan's position in 1944 was hopeless. Japanese engineers understood they were not fighting a more advanced aircraft. They were fighting an industrial system that had evolved beyond anything Japan could match within any reasonable time frame. The human cost of this realization was profound. Japanese industrial workers had labored with extraordinary dedication throughout the war. Japanese engineers had designed brilliant aircraft with the resources available to them. Japanese craftsmen had built weapons of remarkable quality under increasingly difficult conditions. But all of this effort, all of this skill, all of this sacrifice could not overcome the fundamental industrial capacity gap. By late 1944, Japanese military planners understood mathematically that the war was lost. American aircraft production would continue increasing. Japanese production was declining as bombing destroyed factories and raw material shortages worsened. Every month, more B-29 seconds would appear over Japan. Every month, more cities would burn. Every month, the mathematical certainty of defeat would become clearer. Japanese technical officers writing reports about captured B-29 components chose their words carefully. These reports survive in archives. They are clinical, precise, and devastating. The officers noted superior manufacturing quality. They documented advanced systems. They calculated production rates that Japanese industry could not match. And buried in technical language, they wrote their conclusion. Japan could not win this war. Not because Japanese engineers lacked understanding, not because Japanese workers lacked skill, not because Japanese soldiers lacked courage. Japan would lose because American industrial philosophy had proven superior under the specific conditions of total war in the industrial age. End of Part 2. Approximately 4,900 words total. Continuing to Part 3. Continuing script, Part 3. Final. The cultural implications of this industrial defeat extended beyond military strategy. Japan had entered the 20th century determined to prove that Asian civilization could match Western industrial power. The Meiji Restoration had transformed Japan from a feudal society to an industrial nation in decades. Japanese engineers had studied at Western universities, absorbed Western technical knowledge, and returned to build a modern industrial state. By the 1930s, Japan produced aircraft, warships, and weapons that matched Western standards. The Zero fighter had seemed to validate this achievement. When American intelligence officers first encountered reports of the Zero's capabilities in China, they dismissed them as exaggerated. An aircraft with that range, that maneuverability, and that performance seemed impossible, given the Zero's estimated weight. American prejudices about Japanese technical capabilities blinded them to the reality that Japanese engineers had designed something genuinely innovative. The Zero was proof that Japanese engineering could not only match but exceed Western aircraft in certain specific areas. But the Zero and the B-29 represented different philosophies about what engineering should achieve. The Zero optimized for performance within severe weight and resource constraints. Its designers understood they were working with limited industrial capacity, so they created an aircraft that extracted maximum capability from minimum resources. The result was brilliant but fragile, a masterpiece of refined design that required perfect execution to build and perfect conditions to operate. The B-29 represented engineering with different assumptions. American designers knew their industry could produce whatever they specified, so they optimized for survivability and operational effectiveness rather than theoretical performance. They added redundancy because they could. They incorporated advanced systems because their suppliers could manufacture them reliably. They designed for maintenance and repairability because they knew aircraft would be damaged in combat and needed to be returned to service quickly. These different philosophies reflected different industrial realities. Japan's resource constraints and craft-based manufacturing favored designs that minimized material use and maximized performance per unit weight. America's resource abundance and mass production capabilities favored designs that maximized mission effectiveness, even if that required additional weight and complexity. Neither philosophy was wrong in absolute terms, but under the conditions of the Pacific War, where both sides were attempting strategic bombing campaigns requiring heavy long-range bombers, the American philosophy produced aircraft that could execute the mission, while the Japanese philosophy produced aircraft that could not. Japan's industrial response to the B-29 revealed the depth of the problem. Japanese engineers attempted to design interceptors capable of reaching B-29 operating altitudes and destroying the bombers effectively. They produced aircraft like the Mitsubishi J-2M Raiden and the Kawasaki Ki-61 Hien that could engage B-29 seconds at altitude. These were effective aircraft, well designed for their mission, but Japan could not produce them in sufficient numbers. Manufacturing capacity remained the limiting factor. Even when Japanese engineers designed solutions to tactical problems, Japanese industry could not manufacture those solutions at the scale required to matter strategically. By 1945, Japanese factories were producing fewer aircraft per month than they had in 1943, despite enormous efforts to increase production. Bombing, raw material shortages, and the depletion of skilled workforce combined to reduce output even as the need for aircraft increased. The Americans, meanwhile, were producing more aircraft every month. B-29 production peaked at over 400 aircraft per month in the final months of the war. Total American aircraft production in 1944 exceeded 96,000 aircraft. In 1945, even with the war ending in August, American factories produced nearly 50,000 aircraft before production was curtailed. These numbers represented different industrial civilizations. The American economy had transformed itself into a war production machine that dwarfed anything the Axis powers could match. By 1944, 40% of American GDP went to war production. American factories employed millions of workers, many of them women who had never worked in industry before the war. American agriculture had mechanized to the point where fewer farmers produced more food than ever before, allowing industrial mobilization without food shortages. American universities and research institutions had integrated with military production to accelerate technical development. This mobilization required more than resources. It required systematic approaches to manufacturing, training, and quality control that American industry had developed over decades. It required cultural acceptance of mass production and standardization. It required engineering education that emphasized systematic analysis and process design. It required business practices that prioritized output and efficiency over craftsmanship and individual excellence. Japan had industrialized rapidly, but Japanese industrial culture retained elements of craft tradition that limited mass production effectiveness. Japanese society valued the master craftsman, the skilled artisan who perfected his trade through years of apprenticeship. This cultural value produced excellent individual products, but did not scale efficiently to mass production. American industrial culture had evolved differently. American manufacturing had embraced standardization and interchangeable parts since the early 19th century. American engineering education emphasized systematic analysis and quantitative methods. American business culture valued efficiency and output over individual craftsmanship. These cultural factors, combined with abundant resources and vast industrial infrastructure, made America uniquely capable of mass production warfare. The B-29 was the ultimate expression of this capability. $3 billion had been spent developing and producing the aircraft, more than the Manhattan Project. Nearly 4,000 B-29 seconds were built during the war. American factories demonstrated they could design, develop, and mass-produce the most complex aircraft in the world in less than 4 years from first flight to peak production. Japanese engineers studying B-29 wreckage understood they were looking at more than advanced technology. They were looking at an entirely different industrial civilization, one that had achieved capabilities Japan could not match within any realistic time frame. The ethical complexity of this technological dominance deserves acknowledgement. The B-29 seconds that demonstrated American industrial superiority were the same aircraft that firebombed Japanese cities, killing hundreds of thousands of civilians. The March 9, 1945 raid on Tokyo killed more people in a single night than any bombing raid in history. The industrial capacity that produced the B-29 made this devastation possible. American strategic bombing doctrine had evolved toward targeting civilian populations on the theory that destroying enemy morale and industrial capacity would end wars faster. Japanese civilians paid the price for their military leadership's decision to initiate wars of conquest, but they paid in suffering that moral philosophy has struggled to justify ever since. The B-29 seconds that demonstrated the superiority of democratic industrial capitalism were also the aircraft that dropped atomic bombs on Hiroshima and Nagasaki, killing over 200,000 people and introducing nuclear weapons to warfare. Technological superiority does not confer moral superiority. The industrial civilization that produced the B-29 also produced weapons of unprecedented destructive power and the strategic calculus to use them against population centers. These moral complexities cannot be separated from the technological story. The same systematic engineering and industrial capacity that Japanese engineers found so impressive also enabled mass destruction on scales previously unimaginable. The same quality control systems that produced precision aluminum panels also produced the weapons that turned cities to ash. Yet the industrial philosophy the B-29 represented would shape the post-war world in ways that transcended the immediate horror of strategic bombing. After Japan's surrender, American occupation authorities brought American industrial experts to teach Japanese industry modern mass production techniques. W. Edwards Deming, one of the pioneers of statistical process control, taught Japanese engineers the quality control methods that had made American wartime production so effective. Japanese industry absorbed these lessons thoroughly. Within 2 decades, Japan had transformed itself from a defeated nation with shattered industry to one of the world's leading manufacturing powers. Japanese companies took American mass production techniques and refined them further, developing approaches like just-in-time manufacturing and total quality management that would eventually flow back to influence American industry. The industrial defeat of 1945 became the foundation for Japan's post-war industrial renaissance. The B-29 fragments that Japanese engineers examined in 1944 thus represented not just military defeat, but a glimpse of an industrial future that Japan would eventually embrace and excel within. The systematic approaches to manufacturing, quality control, and process management that made the B-29 possible would become central to Japan's post-war success. But in 1944 and 1945, Japanese engineers examining B-29 wreckage saw only the impossibility of their situation. They saw aluminum panels machined to tolerances they could not match. They saw quality control, consistency their factories could not maintain. They saw evidence of production scale their industrial base could not approach, and they knew what this meant. The war would continue until Japan's cities were destroyed and its people exhausted. Not because Japanese soldiers lacked courage, not because Japanese engineers lacked skill, not because Japanese workers lacked dedication. The war would continue until complete defeat because Japan was fighting an industrial system that could produce weapons faster than Japan could counter them, and that gap was unbridgeable through any amount of effort or sacrifice. One Japanese engineer, whose name was not recorded in surviving documents, reportedly walked away from a particularly thorough examination of B-29 wreckage and said something that a colleague noted in his personal diary. The diary surfaced in Japanese archives decades later. The engineer had said, "We are not fighting American pilots, we are fighting American factories, and you cannot shoot down factories." This observation captured the essence of what the B-29 taught. Modern industrial warfare was not primarily about tactics or courage or even technology. It was about systems, about industrial capacity, about the ability to produce weapons in quantities that overwhelmed the enemy through sheer scale. The B-29 Superfortress was not just an aircraft, it was proof that industrial democracy, when mobilized for war, could produce weapons in quantities and qualities that traditional warrior societies could not match. It was evidence that systematic engineering, statistical quality control, and mass production could defeat craft tradition, individual skill, and warrior spirit. It was demonstration that the future belonged to industrial systems rather than individual excellence. Tens of thousands of B-29 seconds survive in museums and private collections worldwide. When you stand before one of these enormous aircraft, you are looking at more than a historical artifact. You are looking at the weapon that taught Imperial Japan a final lesson about modern warfare. You cannot defeat an industrial democracy through conquest, because democratic societies, when threatened, can transform their economies into weapons-producing systems on scales that authoritarian states cannot match. The assembly lines that built automobiles in peacetime built the B-29 inches wartime. The factories that made refrigerators made aircraft components. The workers who built consumer goods built the weapon that demonstrated the ultimate power of mass production civilization. The engineers who designed household appliances designed the systems that made the B-29 possible. Japanese engineers were right to fall silent when they examined that crashed B-29. They were not just looking at superior technology, they were looking at their future, and they found only mathematical certainty of defeat. The B-29 did not just win battles, it ended arguments, it closed debates, it answered definitively the question, what happens when you challenge an industrial society that values systematic production, consistent quality, and overwhelming scale? You lose. Completely, inevitably, mathematically. The fragments of crashed B-29 seconds scattered across Japan in 1944 and 1945 were not merely wreckage. They were messages written in aluminum, declarations that American industrial philosophy had proven superior under the conditions of total war. Japanese engineers who examined those fragments became unwilling prophets of their own nation's defeat, understanding months or years before the surrender that the war's outcome was no longer in doubt. They opened crashed bombers and saw the future, and the future was inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.